Hello and welcome back again to our channel, Tutoring Made Easy. In today's video, we're going to look at sets and surds. We want to have a comprehensive lecture on sets and surds. We have previous videos on sets and surds already, but we feel like we want to have a one-go get-to video where when you get in there, you have all the things on sets, you have all the things on surds, and we're going to solve couple of examples and maybe some practice questions so that it can serve all purposes for you. But I hope you're doing well. Now let's jump straight into it. All right, so we're going to first look at the topic sets, and then later we'll look at the topic. The first section is going to be on sets, and later we'll talk about sets in this video. Now, what is a set? What is a set? We say that a set is a well-defined collection of objects of the same kind. It's a collection, well-defined collection of objects, and they're of the same kind, of objects of the same kind. So, for example, you can have the colors of the rainbow. You have the colors of the rainbow. They are the same kind. You have a set of rainbow, and in it, so let's say rainbow colors. Let's say rainbow colors, and then inside the rainbow colors, the set, you're gonna have the red color. You're gonna have orange. You're gonna have yellow. You're gonna have green. You're gonna have blue. You're gonna have indigo, and then you're gonna have the violet color. So this gives you a set of what? Rainbow colors. They're the same kind. Then you can also have maybe a set of the first six alphabets. The first six alphabets. So that set is gonna have A, B, C, and A, B, C, D, E, and I think F. Like it says, the first six alphabets. Now, how do we have something called a set notation? Let's say a set notation. We have something called a set notation, and we say that a set is denoted or represented by a capital letter. So it is represented by capital letter. So we can say that the set A is maybe a set of the first six alphabet, which is A, B, C, D, E, and F. So it's always denoted by a capital letter. Now, then the next thing we can talk about is the elements, or the members of the set, and they are the components or objects in the set. They are the components. So they are the components within the set. So in this case, this A, B, C, D, E, F, this red, orange, yellow, green, blue, indigo, violet, those are what we mean by the elements or the members of the set. I hope that is clear so far. Now let's quickly look at maybe let's say Venn diagrams. Venn diagrams, and a Venn diagram is just a diagram that depicts a set. So it's a diagram that represents set. So it's a diagram. It's a diagram that depicts a diagram that depicts sets. A diagram that depicts sets. So instead of writing them, let's say we have set A, which is maybe the first 2, 4, 6, and 8, the first four even numbers, and let's say we have set B, which is maybe the set A, B, C, D, and E, and then you have the set C, which is maybe the first numbers 1, 2, and 3. Right? We can be able to say that we can be able to put them in like a Venn diagram. Right? We can put them in the Venn diagram like this, where we have set A, maybe set A is here, and then set A will have 2, 4, 6, and 8 inside, and we can have a triangle with which is set B, which is A, B, C, D, and E, and then you can also have maybe a square to be set C, which is 1, 2, and 3 in the like, and that gives us a Venn diagram depicting what we intend. So we've looked at the definition of set, and we say it's a collection of objects. It's a collection of, and we've also been able to look at the notation. And we said the notation is always denoted by capital letter. And then we also looked at the Venn diagrams, and we said that Venn diagrams can represent sets, and we said that elements and members, they are the components of the set. They're the component of the set. So now we're quickly going to be looking at types. There are different types of sets. There are different types of sets, and the first one is known as the finite set. A finite set, a set that is finite. That means it has an end. A set has an end. So let's say you have a set that says 1, 2, 3, 4 to 5. It's closed. It's closed, so it's finite. It has an end. The end number is 5. But if we look at an infinite set, it is not closed. So you can have it. It could be an infinite set. Could be 1, 2, 3, 4, 5 to 6, and then we don't know where it is going to end. We don't know where it actually ends, and it's closed like that. So because we don't know what is here, yes, this place is unknown. It is known as an infinite set. An infinite set. Now the next set is known as the null or an empty set. A set that is empty, there are no members or there are no elements, there's nothing inside, and it's usually denoted as this, or it is denoted as that, and a set that is empty, or it's a null. So this is normally the null, a null set, and this is what it's called an empty set, and they are the same. They don't have any member at all belonging to the set. The next set we can also talk about is what we call the unit set. A unit set is a set that has only one member or one collection, one member or one element. So maybe you have the set A, which has a member, let's say 2. So this is a unit set. It has only one member. Unit set has only one member. Only one member. And now the next one we're going to look at is what we call the subset. A subset. A subset. A subset. And we're saying that if you have some members in a certain set, let's say set A has members 1, 2, and 3. And let's say set B has numbers 1, 2, 3, 4, and 5. We can see that the members here are all in B. So it means that set A, we can write this as set A is a subset of B. That means A comes under B. It's a subset. And this is a symbol. So in as much as we have the null, we said the null is this, and we said the empty set. An empty set is that. We said that a set can be denoted with a capital letter. Same way, when we talk about a subset, then we are looking at this symbol right here. We are looking at that symbol right there. I hope that is clear so far. Now, the next one we're going to look at is what we call the universal set. The universal set, I call it the mother set, the set that all other sets are under. So it's a set of all members or elements under discussion. It's a set of all members or elements under discussion. So every other set is under it. Is under it. So that's why it's called universal. It's like a global set. Every other set is under it. And the symbol is usually denoted as something like this or something like that. So we said that we have a subset. This is a subset. We have a set notation with a capital, and when we have what? A unit set, which is only one member. We also have a null set or an empty set, and now we are having a universal set in this form. That is a set notation for a universal set. So usually we can have a Venn diagram like this. Okay, you can have a Venn diagram like this. You have two sets in here, and then you can see that if this is set A and this is set B, this is the universal. The square or the triangle you're seeing here is our universal set, and you can see that set A is in what is a subset to the what universal, and set B is also a subset to the universal set. You can be able to witness that. Now the next one we're going to look at what we call equal set. We're going to look at what we call the equal what set. An equal set. Two sets are said to be equal if they have the same members. So they have what? Have same members. And we said the members are the same as what? Elements. The same members or elements. So if you have set A, and this set A is 2, let's say 2, 3, and 5, then set B If we have 2, 3, and 5, and set B is also, let's say, 5, 2, and 3, we can see that they are the same. They are the same members. They are the same members. You can see that here. This is here. That 3 is here, and this 5 is there. They are the same members. They have same members. So because of that, they are equal. They are equal. You can be able to see that. Now the next one is what we call the equivalent set. An equivalent set. Two sets are said to be equivalent if they have the same number of members. So this one, they should have the same number. Have same number of members, or same number of what, elements. All right, so we can say that, let's say we have set A to be 2, 3, and 5, and then we also have set B to be 11, 12, and 13. You can see the members are different. There is no 2 in here, or 3 or 5 in there, right? They are different. However, this has 3 members, and that also has 3 members. So we can see that they are equivalent. They are the same. So they're equivalent. But with equal sets, the members have to be the same. So don't let us forget about that. We shouldn't forget quickly about that. Now the next thing we're going to look at, the next type of set we are going to be looking at, is what we call the intersection. Intersection of sets. The intersection of sets. Intersection of set, and it is usually denoted by this symbol. This is an intersection. Remember, we said that this is the subset. Don't forget that. We said this is null. We said this is empty. Okay, and we're saying that now. We're saying this is what, intersection. And then we're also saying that that is the universal set, which is also the same as something like that. They're the same. All right. So that's intersection. The intersection is where you have a same member belonging to the same set. So let's say you have set A has 2, 3, and 5, right? And then you have set B having, let's say, 5, 6, 7. And you can see that this is common to both of them. 5 is in this set A, and 5 is also here. So that is the intersection. So when we say A, where does A and B intersect? They intersect at this member. They belong to the same set. So the member 5 is in one of the sets, and that's also at the same time belonging to another set. So the set of objects which belong to set A and at the same time they belong to set B is called the intersection. Now let's also look at how we can look at it. If we see it, how do we know? Maybe in a Venn diagram. In a Venn diagram, for example, let's say you and I have something like this, right? So where they meet, we can tell that where they are meeting is here. Here, you can see that this set, the ring comes into this set here. And this set also, the ring comes in here. So they all meet in here. So this side is what we call the A intersection B. That's where they meet. That's where they meet. And I hope that is a bit clear. Now we're going to look at maybe the union. We're going to look at the union, or the union of sets. Okay, let's quickly look at the union of sets. So with the union of set, union of set, we're saying that a symbol here is the reverse of the intersection set. Remember, we said that this is intersection. So when you flip that, when we flip it like a valley, that gives us, when we flip it like a valley, that gives us a union. That gives us, and we can also see it in a Venn diagram as this. So if you say a union, when you say a union, when we have something like this, we shade all of it, which is set A and B. That means we are shading everything. That means A union B. That's A union B. A union B. So let's keep that at the back of our mind. Now the next type of set we're going to look at is what we call the complement of a set. Complement. The complement of a set. The complement of a set. And with the complement of a set, if A is a subset of the universal set, then the complement of A is a set of members which belong to the universal set but do not belong to A. So let's say you have a universal set of numbers 1 to 10. Okay? And then we have the set A, which are only what? Let's say even numbers. Okay, even numbers. So what it means is our universal set is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's our universal set. And then our even numbers is going to be 2, it's an even number, 4 is an even number, 6 it's an even number, 8 it is, and 10. So now, when we say what is A, when we are asking for what is A complement, we are saying that what are the members that are in the universal set but they are not in A. They should be in the universal set but not being A. That's a complement. That means not A. Not A. This means not A. Not what is in A. Not what. So what is not in A is 1. You can see what not in A, what is not in A is 1. The next thing that is not in A is 3. The next one too is 5. The next one is 7, and the next one is 9. You can see that. So that's A complement. That's A complement. I hope the complement of a set is clear. Now let's see how that probably will look like on a Venn diagram. Let's look at how it's going to look like in a Venn diagram. Let's imagine we have this Venn diagram here. We have this Venn diagram here. We have the two. We have this is set A. Let's say this is set A. So that means that A complement is not what is in A. A complement is not what is in A. So here, this side, whatever is outside the ring, the right ring, is the A complement. Whatever is the A complement. A complement, because this is A. Okay, this is A. All this is A. So anything outside it becomes what? A complement. A complement. I hope that that works. Now we're going to look at certain properties. We're going to look at certain properties of sets. We're going to look at certain properties of set. And I believe the first one is what we call the commutative uh, property. And to conclude that property, we are saying that when we have A intersection B, it should be the same as B intersection. That means order doesn't matter, or the arrangement doesn't matter whether B is here or A comes first. We are going to get the same thing, especially if it's an intersection. The intersection is common among them. Then A intersection B will always be equal to B intersection A. So let's imagine. How do we know that? Let's imagine that we have a set A with 2, 3 with members or element 2, 3, and 4, and we also have set B with elements or members 1, 3, 5, and 7. Now, our A intersection B, what is common is 2 here? No, 2 is not in there. Is 3 here? Yes, 3 is there. So 3 is intersected, but 4 is not. There's no 5, no 7 among them. So this becomes A intersection B, and this is, don't forget, this is called what? A unit set, because it contains only one member. Can you see that? Now the next thing is to flip it. B intersection A. Where's our B and intersection with A? It's going to be the same thing. Whatever is in B and is in A is going to be the same 3. It's going to be the same 3, sorry. And that still gives us what? A unit set. And we can see that no matter whether we start with A intersection B, it is the same as whether I'm starting B and A. And that makes it what? That makes this the same, and that makes this property satisfied. So the commutative property says that A intersection B is always going to be equal to B intersection A. Now it also holds for the union, for the same property. So if you have, let's say we are looking for A union, let's say we are looking for A union B. A union B is to join the A and the B together, and to join it, we are going to get 1, 2, 3, 4, 5, and 7. That's A union B. Now, if we want to do B union A, it's also going to be the same thing. It's going to be the same. It's going to be the same. That means that for commutative property, so we can say that commutative property, a set is said to be commutative if A intersection B is equal to B intersection A, and also if A union B is equal to B union A. So we are okay with the satisfaction of the commutative property. Now let's look at the other type of property, which is known as the associative property. Yeah, I hope everything is working smoothly so far. Please, if you haven't yet subscribed to our channel, please do us a favor by supporting us so we can grow this channel together and to help as many people as possible. We want to make tutoring very, very easy and comfortable. We begin with math journey, we'll go to probability journey, we'll go to statistics journey, we'll go to physics, chemistry, biology, so that everybody around the world can have a get to platform to study and to use it as a tutorial while they are taking their classes. We'll be doing questions, also separate videos on questions as well. So please support us. And if you're already a subscriber, we thank you for supporting us. And thank you. We're going to continue with associative property. And um, with associative property, all we are saying is that if you have A intersection B intersection C, we are saying that is the same as A intersection B intersection C, like this. And if you also have the second one, this is the first one of the associative. The second one says if you have A union B union C is the same as A union into B union C. So we're going to use the Venn diagram to see if we can prove this. So let's imagine that we have a Venn diagram like this here, and then we have, let's say, three rings in there because we have three sets in there. So these are three rings. Now, what is going to be our A intersection B? This is A, this is B, and this is C. Our A intersection B is the whole of this side because the ring A and B. This is where they meet. Now, also intersecting with what? C. So basically we have to shade the whole of what? We have to shade the whole region of C. The whole region of C. You're saying that the A intersection B, the yellow region, how does it intersect with the whole of C? So if this is the whole of C, the way to intersect will be both red and both blue and gold, or blue and yellow. So the intersecting point is going to be this. It's going to pretty much be this. This is how it's going to look like, in all fairness. So we're having three rings like this. We have A, B, and C, and we are realizing that the red, gold, green is here. Yeah, sorry, the blue and gold, is here. It's only this region. I don't know whether if you can see it. It's only this region because here you have blue and gold here, over here, blue and gold. So that's that region. That's A intersection B, also intersecting with C. Now let's do here on this side of it to prove it. So here too, over here, we're going to have three rings as well. Three rings as well. We have our A, we have our B, we have our C. Now, B intersection C is this region here. B intersection is going to be the whole of this region here because this is the ring B. This is the ring C. You can see there's a ring C. Was this coming from here? So there's a ring C, and then there's a ring B. The down part, this side of the ring what? B. So we've gone into it. This whole side is the B intersection. But now the B intersection C also intersecting with A. Also intersecting with A. Also intersecting with A. So what's our A? Our A is intersecting with all the side here. It's intersecting with all the side here, like that. Intersect with everything that is here, like this, like this. And we can see that clearly, they are all intersecting in the region of both the blue and gold. Can you see that, please? Can you please see it? It's right there. And the blue and gold region is here. It's in the middle, right here. So we can see that we have been able to prove that this side is the same as that side. So A intersection B also intersecting with C is the same as A intersecting with B intersection C. So we've proved the first part of it. Now let's quickly look at A union B union C. What we are looking at here is pretty much having our first diagram here like this. First diagram with our three rings like this, and inside we're going to shade. So here we have A, B, and C. Now the first part is A union B. A union B is the whole of this region. The whole white region is A union B. We're shading the whole of A union B, and we want us to bring it together with they wanted to do it together with to unionize it with C. And to do that, to unionize with C means we have to shade the whole of C. So the whole of C is that yellow region. Now, but the interesting thing is that we want both. We are looking at both A union B unionizing with the C. So it's both the white and gold regions because you are bringing all of them together. That's the idea, bringing everything together. This is A, B, C, and to bring everything together it means we are shading the whole of A and B and also shading C because we want to make C also join the union of A and B. You can see that. Now we're going to continue drawing the second part, this side here, where we have our other set here. We're having three circles again. Yes, set A, set B, and set C. And we can see that this B union C and B union C is joining B and C together, which you see what we are doing here, joining B and C. And then they want us to add set A to it, and to do that we shade a whole of set A, and we can see that the whole region we can see that the whole of A union, the A unionizing with B union C is all the white and yellow region, if you can see that. So you have three circles like this. You have set A, set B, set C, and then we are going to be able to shade everything to represent A union B union C. And we've been able to prove that associative property holds for both the intersection and the union of a set. Now let's look at the third type. We looked at the commutative property, we looked at the associative property, and now we're going to look at the third type of property. And that third type of property is known as the distributive property. The third one is known as the distributive property. The distributive property. And what does it say? The distributive property says that if you have A unionizing the intersection of B and C, they're saying that it's the same as A union the B intersecting A union C. That's the first one. That's the first one, just like we did for the for associative property. And then the second one says, if you have, let me use what color? I think I should use green. It says if you have A intersecting with B union C, we're saying that it's equivalent to A intersection B union A intersection C, like this. Beautiful. Beautiful. So now we can have our first Venn diagram here. First Venn diagram with our three yellow rings, like this. And then the first thing we're going to do is pick this B intersection C. This set A, B, and C. So B intersection C is going to be here because this is the region B and C. So we are shading that's our white region, B intersection. But we want us to unionize it with A. Join the intersection of that with set A. They want us to join with set A. But where's set A? Set A is this region. This is the whole of set A, the blue region. We're shading because this whole thing here is set A. So we are shading everything with what? Blue. So if we do that, what we are going to generate, what comes out, pretty much, what comes out with our three yellow rings, just be patient with me. With our three yellow rings, unionizing everything with the whole blue region, which is set, sorry, I wanted to pick this number. The whole of this blue region, which is set A, because they wanted us to unionize it together, right? Together with this B intersection C region, and the B intersection C region is the whole of this side. So basically, the whole of A and then this side is what we are looking for to prove. Now let's draw the second part here. The second part is here. We're going to still have our three yellow rings. Set A, set B, set C. Now this first one says A union B. We want to join the whole of A union B, and it's like this. Yes, we are joining the whole of A union B. We are joining A together with B, and that's what we have done. We've brought A and B together. We fused them together, and then they also want us to bring A and C together with this one here. A union C. Where's A union C? Well, let's use blue. A union C is here. This is A joining C. This is the whole of region of A joining C, right? The whole of A joining C. A and C, bringing them together, right? We bring them together, and now they want us to see where they are intersecting. And to see where they are intersecting, if we draw, let's say I'm using a blue. If I draw this, where do they intersect? Where do they meet? Where do they meet? These are three rings. And we can see that they meet where we have they meet where we have both the white and blue, right? If you can see that, white and blue, and the white and blue is this region here. Let me use the blue. The white and blue, you have blue all over here. If you can see it with white inside it, this whole region here, you can see there's white and blue there. And then here too, you're seeing white and blue as well, this side here. So we've been able to see that this is the same as that. They are the same. And we have been able to prove that. Now we're moving to the next side here, where we are going to draw our first Venn diagram with our white rings this time. White rings this time. And then we say that this is set A, set B, and set C. And we're saying that this B union C. B union C is this side. B union C. The whole of B and C. This B union C. We're shading the whole of C and B together. And then we want to make sure that they are intersecting with A. Where does it intersect with A? I'm going to pick green. So this is A. Set A is the whole of this region here. And you can see that they intersect here. On this region right here. Like that. So let's say that we have a ring here for that one. And then we have 3 yellow rings. We are saying that they are intersecting where? Where do we have the green and yellow? And the green and yellow is here. And then we also have green and yellow there. We also have green and yellow also this way. And then that's where they all intersect. So this is the region for A intersecting with B union C. Now let's look at this side. When we're looking at this side here, we are having 3 rings. In 3 rings. And we have set A, set B, and set C. And you can see this set A and B, intersection B is this region here. Right? And A intersection C is this region also. A intersection C is the whole of this region. And they want us to join it. We're not intersecting. We want us to join it. And to join that, let's first have our yellow rings. Let's say yellow rings. We want to join them together. And to join them, it is this white coming up. And both this white and blue. And then the only blue here. So because we are joining all of them together. And we can see that this is the same as that. And we've been able to complete the distributive property. So we've said that there are 3 types of properties of set: the commutative property, the associative property, yes, the associative property, and the distributive property. And I hope what we've done so far kind of helps. It's kind of helping you and I to be able to solve math problems. Okay, so now we are going to be solving Venn diagram questions. I'm going to take maybe 2 questions on set on 2 set problem, and also we're going to look at the 2 set problems. So let's say we're going to look at, let's say we said we are going to look at Venn diagrams. Let's look at Venn diagrams. Okay, Venn diagrams. And in this Venn diagrams, we're going to look at the 2 set problems, and then 3 set problems. Okay, so we're going to do that. So let's take a question. The question we are having, it says, in a class of 40 students, we have 40 students. A class has 40 students. All right, a class has 40 students, and it says that 30 read mathematics. So mathematics is read by 30 students. Okay, 30 read mathematics and 20 read English. And English is read by 20 students. Okay. Each student reads at least 1 subject. Each student reads at least. Whenever you hear this, each student will get there. Each student reads at least 1 subject. It means something. When we get there, we'll talk about it. Now the question says, how many? How many students? Okay, how many students read math and English? How many read math and English? Now, to solve this problem, right here, what we're going to first do is do some little bit of set notations here and there. All right. So we're going to say that we will let X represent members. Okay. We're going to make it, let's N. Let's use N rather. Okay, sorry about that. Let's use N. Let N be equal to the members or elements of the sets. Okay, and then we can also say that let this be the universal set. Okay, so that, and then we can also say that let M be students who read mathematics, and then we let E be students who read English. And we're also going to let maybe X be students who read math plus English. All right. So if that's the case, we can say that the number, this is the n, is the number of elements of what? The universal set is the class of students. Okay. The number of that, we've been given that to be 40. Now, what's also the number of mathematics students? We've been given that to be 30. And the number of English students, we've been given that to be 20. And then the number of both math and English, we've been given that that's supposed to be what? X. We said we're going to make that one X. So now we are going to draw our what? We're going to draw our Venn diagram. Going to draw our Venn diagram, and we're going to have our 3 rings like that. Okay, 3 rings, and then we can see that this is mathematics, and it's about 30 students, and this is our English. It's also about 20 students, and then we have the what? The universal set, which is about 40 students. So everything in the box, they need to add up to what? 40. Now remember, we said that if they say that this thing that I told you, we're going to come back to that. Each student reads at least one subject. It means that you can't find anybody outside this box. Everybody's in either in M or E or both. At least one subject means that you are either reading one subject or you are reading more than one subject. At least means minimum one or more. So either you are inside the rings or you cannot be outside the rings. You are just inside the rings. All right, so let's keep that in mind. The moment you get any clue like that in an exam question, it is telling you that you're never going to get anything outside the rings. All of them are inside the rings. And remember, we said that we're going to make here to be X, right? This is it. X is both. This region is both mathematics and English. Now, if here is A and B, it means that for mathematics, which is 30 students, it's supposed to be equal to A plus X. Can you see that the region A and X gives us the whole of 30? Can you see that? But we're looking for A, so we can let the A stand there alone and bring this X here, and it will change. This sign will change to minus X is equal to A. So A is 30 minus X. So this region is 30 minus X. Now for English, we are saying that the English is 20. And that is also B plus X. All right. And we want B to stand alone. So we make this X come here. So we're going to get 20 minus X is equal to B. Therefore, B is equal to 20 minus X. B is equal to 20 minus X. Now, we know that there's nothing outside the ring. So here's 0. Nobody's outside. So now we can say that our 30 minus our X, this one here, plus our X, this one here, plus our 20 minus X will all add up to the universal set. Will all add up to the universal set of 40. Because everything that is in this box should give us the 40. Now, if we look carefully, 30 minus X plus 20 minus X, we can see that this minus X and this plus X will be 0. And we're going to get 30 plus 20 minus X is equal to the 40. Now, 30 plus 20, this 40 can come here. We're going to get minus 40, and this X can go there. We're going to get plus X. Therefore, we're going to get 50 minus 40 is equal to X. We can say that, therefore, X is equal to 10. If X is equal to 10, then this side is 10. And if this side is 10, A becomes what? 20. And if here is 10 and here the whole of this is 20, then B is also what? 10. And we can see that the 20 plus the 30 plus the 10 will give us the 40. Can you be able to see that? So the question says, how many students read both mathematics and what? And English. And it's the one in the middle here. It is the 10. It is the 10 that we have been able to look out for. So I hope this helps. And then we are going to move on to a three set problem. We're going to look at a 3 set problem, and then we can maybe bring the curtain of sets down. No, I think we'll look at maybe the De Morgan's laws. We'll quickly look at De Morgan's laws quickly, and then maybe we'll transition to maybe sets or something. So I'll quickly do the three set problems. Three set problems. So we have a Venn diagram again. Venn diagram. Sorry. And we are trying to do a three set problem. Okay. A three set problem. A three set problem. So let me look for a question, and then we can all together try to solve this problem. I think I have one here. I don't know. I don't think so. Yeah. I think I have one here. Yeah. We've got one. One beautiful one here. All right. So there's a question here. And the question is saying that, is asking, it says in a class of 40 students, so we have a class of 45 students. Okay. We have a class of 45 students. And it is known that 24 of them do art. So art is 24. Then 20 do chemistry. So chemistry is 20. And 22 do biology. So let's say biology becomes 22. All the subjects do at least one subject of the one of the three subjects. So don't forget what it means. All the students do at least one. So it's saying that all students do at least one of the three subjects, while 7 do art and biology. Okay, so it says that 3 do all. So let's say 3 do all. It says all 3 is equal to 3. Then it says that art and biology, art plus biology is 7. And then art and chemistry, but not biology, art. 6 do art and chemistry. So there's art and chemistry, but not chemistry. And that is not chemistry is 6. And then he says that 8 do chemistry and biology. So we have chemistry and biology, and they're saying that is 8 people. Now let's start putting in the notations. So I think that the first notation we're going to say is that we can say that let n be the number of members. Okay, it'll be the number of members or elements. All right, and then we can also make a number of members or elements. And we can also say that we can let this be the universal set. And what's the universal set? It is the class of students. Class of 45 students. And then we're also going to continue by having A to be what? Art students. Art students. We're going to have C to be chemistry students. And B to be bio students. Okay. Now, it says all students do at least one of the three subjects. All 3 is equal to 3 people. So we are saying that A intersection. Okay, so let's say that, let's begin to do the notation properly. So we're going to have, let's say, the number of the universal set, the number of class people is 45. Then we also have the number of the art student is 24. We also have the number of the chemistry student is 20. And then the number of the biology student is 22. And we also have the number of A intersection B intersection C is 3. We also have the number of art and biology. The number of art and biology, but not what? Art and biology only. Sorry, art and biology only. Art and biology only, it gives us 7. And we also have art, the number that study art and chemistry, but not, sorry, let me take my time. I think I'm rushing. So let's say that the number here, we're over here. The number that study art and chemistry, but they don't art. Oh, let me take that question again. The one that is 6, it says that 6 do art and chemistry, but not biology. So this is not biology. So we are saying that art and chemistry are not biology. No, this is not biology. The end is not biology. Okay, and we're saying that that is 6. And then we also have 8 do chemistry and biology. 8 do chemistry. So the number that does chemistry and biology is 8. Now I'm going to represent this on the Venn diagram. How do we do this representation? We can take this red color here and do a nice work here. And then we're going to have maybe our rings, 3 of them. Okay, and we're going to have this is set A, set bio, and then set chemistry. And the A there is our art. And we're saying that this is our universal set, and we said it's how many? It's 45 students. It's 45 students. So we've done this. And then the set A is 24. We've also done that. The set C is 20. We've also done that. The set B is 22. Done that. Now it says the number of all 3 is this side. Is 3. Here is going to be 3. And the number of A and B, the number of A and B is 7. So you're saying this, you remember this is the whole of A and B. Should be 7. But already we have 3 here. So that means here is going to be 7 minus the 3, which is 4. Okay? So that we know that this region from here to here is 4. And then the 3, then they'll all give us 7 to represent both art and biology. I hope this clarifies stuff. All right? Now, the next thing we're going to do is that they're asking us that the number of art and chemistry. Where's art and chemistry? This region here, this region here is art and chemistry. Art and chemistry. And they're saying that the art and chemistry, but not biology, is 6. So you see, if you look at this, the art and chemistry, but there's biology inside. This one is the biology that is inside. So we take that one out. You say that the art and chemistry and not biology is 6. So here is 6. Here it becomes 6. Now it's also saying that the number of biology and chemistry. The number of biology and chemistry. So this is biology and this is chemistry. The number of biology and chemistry is 8. And where's our biology and chemistry? Our biology and chemistry this side. Let me show you. This is biology. This whole region, or let me use maybe something different, maybe green. This whole region, you can see, is biology. Can you see that? Sorry. This region is biology and chemistry. This region, biology and chemistry. But there's already 3 there. But they said that whole region is supposed to be 8. So here it's going to be 5. So that the whole region becomes 8. Yes. So that the whole region becomes 8. Now, we can see clearly that we can be able to find what is here. Can you see that? We can be able to tell what is here because here is 4. Here's 3 and here's 6, and that gives us 4 plus 3 plus 6 is 7 plus 6, which is 13. Now we want to make sure that the A is 24, right? The A is 24. So we're going to get 24 minus the 13, which gives us 11. So it means here alone is 11. Only that place is 11. Now the next thing is this side. We have 4 plus 3 plus 5. This side here. Yeah. 4 plus 3 plus 5, which is going to 12. 7 plus is 12. And that 12, we're going to take it from this 22. So it's going to be 22 minus 12, which is equal to 10. So here becomes 10. Here becomes 10. The next thing is that we have 6 plus 3 plus 5 is going to be 9 plus 5 is equal to 6 plus 3 plus 5 is going to be 9 plus 5, which is equal to 14. So here becomes 14. Now the questions are going to follow. The questions are going to follow next. The question says, how many do biology only? So we are looking for biology only, bio only, or chemistry only, chem only, or art only, or art only. We are looking for that first question. All right. So we are going to see we're going to realize that there are 10 students that do biology only. Right. You can see that if you look at this region is a biology only. This region is biology only. So bio only is 10. You can see that. And chem only is 14. Chem only is it chem only? Is it 14? Am I doing something wrong here? I think it's not. So here it's going to be 6. Sorry. Here it's going to be 6. The 14 region is going to be 6. It's going to be 6 here. So that everything gives us the 20. So the chemistry only is 6. And then 7 plus 13 which is 7 plus 6 13 minus 24, which is 11, will be the art only. Art only. So bio only is 10, chemistry only is 6, and 11 students they only read art only. The second question says that find those as two subjects only. Two subjects only. So we are looking for two subjects only. Then if you are here, you are doing two subjects only. If you are there, two subjects only, you're doing two here. Because when you are here, you are only doing art and biology. If you are here, you're only doing art and chemistry. If you're also here, you are doing only chemistry and biology. And then that's going to give us 4 plus 6 plus 5, which is 10, plus 5, which is equal to 15. I hope this was helpful. I hope this was helpful. Now we're going to look at probably the De Morgan's laws. Um, the De Morgan's laws. I don't know whether you are familiar with what we call the De Morgan's laws, but pretty much this is what we mean by the De Morgan's laws. The De Morgan's law says that sorry says that if you have A union B, if you have A union B complement, I think yeah, sorry, if you have A union B complement, right, is the same as A complement union B complement is the same as A complement intersection B complement. I think so. I think so. All right. If you have A complement union B complement, the same as A complement intersection B complement. If you also have what do you call it? Let me see. Give me. If you also have and vice versa, so they are the same. Pretty much they are the same. If you have A complement union B complement, you are going to get the same A complement intersection B complement. So let me take it again. Let me take it. I think I'm not taking it well. So let's take it again. For De Morgan's laws, we are saying that if you have A union B all complement, we get A complement intersection B complement. Now over here on this side, if you have A intersection B all complement, we are saying that it's going to be equal to A complement union B complement. I hope this is clear now. So now let's see if we can quickly use Venn diagrams to prove this a little bit. All right, and then we end the set topic and we move on to surds. Now let's say that we have this box here, this Venn diagram here, with our three rings. No, with our two rings. Sorry, it's two rings because you're dealing with only two sets here. Sorry about that. So let's say that this is our Venn diagram, and we have two rings here. Now they're saying that A union B. This is A union B. Remember, if this side, if I shade inside, sorry, if I shade inside like this, because this sets A and B. If I shade all the white region is what we call the white region is A union B, is the white region. So anything outside it, maybe the green, anything outside is the complement of that. That means it is inside the universal set because this is a universal set. So anything, the green region is A union B complement. Yes. Anything, or I can make the inside here the white region. That is A union B is the white region. Yes, A union B will be the white region. And then the complement is the green. So anything outside it is the what? Is the A union B complement. So this one is green, and then the A union B is white. Can you see that? It's white. So this is our answer. This is what we are interested in, this one here. The shaded region is the green. That is A union B complement. Now let's look at this side here. If we have another two rings here, we have two rings again, two rings, but this time set A and B, right? And we want A complement. A complement is, let's say, the white region. Where's A complement? A complement anything outside of the region A. Anything outside of it. Anything outside of it is the region A. Now, we're going to take the green and say that we also want a B complement. B complement is anything outside B. Anything Outside of B, we can't shade B. So anything outside of B is our B complement. Can you see that? Yeah. Anything. Yeah. Anything. Anything outside of it is our build B complement. Now we are looking for A complement and B complement, right? So A complement is our what? White region. Don't forget that. So let's write it that way. Let's write it that way. We can say that our A complement is the what? Is the white region, and we want to intersect it. We want to intersect it with what? With our B complement. Our B complement is the green region. B complement is the green region. And where are they going to meet? They have to be both white and what? And green. They have to be both white and green. So the white and green is this section here. If you let me draw it again for you to see. Okay, the white and green is outside. The white and green is outside. Can you see that? The white and green has been shaded outside. Here, there's no. Here, it's not. It's not white and green. This side is also nothing is there. Here's only white, but outside you can see it is what? White and green, and you can see that this is equal to this. This is what we shaded outside. It's equal to whatever is going on here, and we've been able to prove the De Morgan's law for that one. Now let's try this side here. We want two rings, and we want what? A intersection B complement. Now this is A intersection B. The yellow region is A intersection. Because this set A and this set B. This is A intersection B. This is where they meet. But the complement of that will be outside it. Anything outside it, outside that yellow region, yeah, it's our it's our that means our A. So let me write this well. Let's say A intersection B is in yellow, but the complement is the green. So the green is our answer, and then we're going to look at over here as well. Let's draw another two sets here, A, B, and then we are looking for A complement. A complement is this white region here. That's A complement, white region there, and then B complement to B complement to is going to be what? This region here. B complement is going to be this region here, maybe the blue region. Anything outside of B, anything outside of B. Can you see that? And then we are going to bring it to what? We unionize it. So we are unionizing the white and the blue. We're unionizing the white and the blue. And if you do that, it is all anything outside of this region. That means this side is not part. But we are shading everywhere except this part. And we can see that that is the same as here. We shaded all the thing outside the yellow, and the same thing, we were shading everything outside of this question mark here. All right, so we end our set topic, and then we are going to move on to surds. We are going to move on to surds. This is going to be comprehensive, so that anytime you come back to set and surds, you have a whole topic, a comprehensive lecture there for understanding. And then like always, you can check our videos. You can see that we've been doing practice questions for each topic. So there are so many questions we've done on sets and surds that you can look through. We'll be doing comprehensive lectures for all the topics, and then we'll continue doing practice questions in the form of shorts. So just be looking through our channel, and you're going to find all that you need. Now we're going to begin with surds. Let me start with a green color. We're going to begin. We're going to continue, and then we are continuing with what? Surds. Sorry. And we said that. Remember when we talked about real numbers? And we talked about rational numbers and irrational numbers. So this is surds fall under the category of irrational numbers. Yes. So if a calculation requires an exact answer, irrational numbers must be left in the surd. Irrational numbers must be left in a surd. They must be left in the surd. Right. So now we're going to look at setting things in surd. Like maybe you're looking at perfect squares. So let's say you have square root of 9. It's a surd, but it's a perfect square, because if you have, it's going to be the same as 3 squared like this, and it's going to be 3 squared, and then the square root is to the power half. Don't forget, the sign square root means to the power half, an exponent of half, and this is going to give us 3 squared times half, and this is going to give us 3 squared times half, And this 2 cancels this, and you're going to have 3 to the power 1, and that gives us 3. I hope that helps so far. Now, let's look at square root of 36, or sorry, square root of 16 is the same as 4 squared, because you're going to have 4 times 4 is 16. That's 4 squared. And that's going to give us 4 squared into what? To the power half, because this is to the power half, which is the same as 4 squared times half, which is equal to 4 times 2 times half. And this 2 cancels it. You're going to get 4 to the power 1, which is equal to 4. Which is equal to 4. Which is equal to 4. So I hope this is, I hope this is helping so far where surds are coming from. If we see things in the form of square roots, then we are looking at surds. Now let's look at how we can be able to add sets together. Sometimes you see addition. I'll say addition and subtraction because they're almost the same. Addition and subtraction of surds, they're somehow similar. Addition and subtraction of surds. So let's say that you have m square root of k plus n square root of k. We are saying that what you can do is to take this and add them. Why can we do that? Because this k, this square root of k, they are the same. So we can add the things by n, the m plus the n together, and just represent this by k. That's it. This can, it is not, please, it is not m plus n square root of 2k. It's not. It's not. Please. It's just square root of k. Please. It's just square root of k. Now for subtraction, for the same thing, let's say m squared of k minus n squared of k, we are looking at same thing. M minus n will subtract, and then we just represent it with a k there like that. That's the rule for addition. The rule for addition and subtraction. The rule for addition and subtraction, and I hope that is a bit clear and okay so far for addition and subtraction. So let's take some quick examples. Let's take some quick examples. Let's say we have 5 square root of 2 plus 3 square root of 2, and what are we going to get? Because this and this are the same, let me put it in white. This square root and this square root, they are the same, so we can add the 5 plus the 3 first and just represent this by 2, and we know we are going to get 8 square root of 2. All right, if we have, let's say we have let's say we have 5 square root of 2 minus 3 square root of 2. Same way, we can see that this square root of 2 and that square root are the same, so we're going to subtract the 3 from it. So we're going to have 5 minus 3 and square root of 2. So this is going to give you 2 square root of 2, and there we go. And there we go. And then we've been able to do addition and subtraction of surds. So addition and subtraction of surds. So based on that, let's quickly look at a problem. Let's say we have square root of 50. You're being told to simplify the square root of 50 plus square root of, let's say, 32 minus square root of, let's say, 162. What do we do? Always pick one of them one at a time. And this 50, you can start with 2 and say 2. What do I multiply by 2 to get 50? It's what? It's the number 25. Also, I'm going to start with 2. What do I multiply by 2 to get 32? It's 16. And the reason why I'm picking that is that this 25 is a perfect square. So we can go ahead with that. We need to have one that is not perfect square and the other being a perfect square. So this 2 is not, but this 25 is. Same way, this could be what? 2 times 81. Now, what are we going to get? We're going to get square root of 2 times square root of 25 plus square root of 2 times square root of 16 minus square root of 2 times square root of 81. We continue and have square root of 2 times square root of 5 squared. Can you see that? Plus square root of 2 times square root of 4 squared minus square root of 2 times square root of 9 squared. And then we're going to have square root of 2 times 5 squared to the power half plus square root of 2 into times 4 squared to the power of half because of the square root sign, please. Then this is going to be a square root of 2 times 9 squared to the power half. Now we're going to get square root of 2 times 5. Why? Because this 2 will cancel that. Plus square root of 2 times 4, because this will cancel that. Minus square root of 2 times 9, because this will cancel that. And we're going to get 5 square root of 2 plus 4 square root of 2 minus 9 square root of 2. And what we're going to have is that you can see that this square roots and this square root, they are the same. So we can add this and this. It's going to be 5 plus 4 minus the 9. They will just add the square root of 2 to it. So we're going to do, this is going to give us 9 minus 9 square root of 2. And that's going to give us 0 square root of 2, which is 0. which is actually 0. All right, which is actually 0. I hope that one is clear. I hope that one is clear. Let's look at maybe multiplication. Let's look at maybe multiplication. Multiplication of surds. Let's say multiplication of surds. And let's see whether that can be helpful to us. So we're going to look at multiplication of surds. So the multiplication of surds. Okay, multiplication of surds. And with multiplication of surds, we can have, let's say, the rules are, if you have, let's say, square root of a times square root of a, it is not square root of a. You remember when we had square root of a plus square root of a, we're going to be, this times this is 1, this plus this is 1 plus 1, and then we bring square root of a. This is not the same as 1, like this 1 here, 1 times this 1 here, and then bring square root. It's not 1 square root of a, it's not. This time around, it is, sorry, when you have square root of a times square root of a, it is the same as a. Why? Because this is a to the power of half, because of the square root, times a to the power of half because of that square root. Now this and this, they are the same. Remember, in indices, the bases are the same. So we add the exponent, so it's going to give us a to the power of half plus half, which is going to give us a to the power of 1, which is a. Don't forget that. So that's where we get to, where we have a to the power of 1 to be a. So that's one of the rules we need to keep in mind when it comes to multiplication of surds. If you also have another rule, if you also have, let's say, square root of a divided by square root of b, it's the same as writing it this way, a over b. The whole square root will take it. All right, so please don't forget something like that. All right, don't forget those rules. Please don't forget those rules, okay? Don't forget the rules. So we are going to take some problems and see how we can be able to apply the multiplication of surds. So let's say that we have, let's say, square root of 3 minus 1. We also have 2 minus square root of 3. What do we do? It means we need to let this one multiply this, and that's going to give us square root of 3 times 2. Can you see that? And the same one can multiply this, which is going to be plus into bracket square root of 3. We are adding. Don't worry, we are adding. So we finish the first one. This times this, we finish close it, plus this square root times this square root here. It's going to be times what? And remember, that square root there is negative square root of 3. Don't forget. Then we bring our plus again. And then the next one is going to be this and this. It's going to be negative 1 multiplying 2. Can you see that? Plus the same negative 1 multiplying negative square root of 3. So it's going to be negative 1 multiplying negative square root of 3. And then we are going to get, this is going to give us 2 square root of 3. And then plus into bracket, we're going to get negative 3. Remember, we said we have square root of a times square root of a, it is just a. Don't forget that. So this time, this square root of 3 times square root of 3 is just 3. And then, but there's a negative sign. That's why I brought the negative sign there. And this is going to give us plus into bracket minus 2. And it's going to be plus into bracket plus square root of 3. Can you see that? Because negative 1 times negative is plus, and then you bring the square root of 3 there. So you're going to have 2 square root of 3 minus 3 minus 2 plus square root of 3. Now, let's rearrange them. 2 square root of 3 will be at one place. This one, we can join it. Plus square root of, the sign doesn't change because we are not crossing an equal to sign. So we are just rearranging it. Then this also becomes negative 3, negative 2. The sign changes when this is crossing an equal to sign. There's no equal to sign that is being crossed. They are all on the same side. Now, because this and this are the same, we add 2 plus 1 together and then bring our square root of 3 here. And then this gives us negative 5. Why? Because you owe 3, and then you owe another 2. So you owe 5. So that's why it's negative. So this is going to give us 3 square root of 3 minus 5, and then we are done. So those are the things you see in multiplication of surds. Another thing you might come across is what we call conjugation. Conjugate a set. To conjugate a surd, let's say you have square root. Let's say we have square root of a plus square root of b. If we want to conjugate it, it becomes square root of a minus square root of b. So don't forget that. Don't forget that. So if we have, let's say square root of 4, okay, square root of 4 minus square root of 5, we are saying the same as square root of 4 plus, the sign changes to square root of 5. If we also have something like, if we have something like 4 minus square root of 5, when we are conjugating, it changes to 4 plus square root of 5. So those are the things we need to keep in mind. Also, remember we studied something called the difference of two squared. The difference, we will use that a lot. The difference of two squares. Maybe I'm just trying to remind you. Remember, if you have something like this, we said that if you have a squared minus b squared is the same as a plus b multiplying a minus b. Do you remember that? Or it can be it can be the opposite. It can be it can be in this form, a plus b like this, a minus b. The moment we see a plus b, the same a here, b there, b there, but the sign is changing. There's a plus here. The negative is difference of two squared. It means a squared minus b squared. So it's either you are seeing this first and you have to change it here, or you are seeing this side first, this side first, and you have to change it to this side, right? So let's keep that in mind. So let's say that you and I have been given something like 4 plus square root of 5, and we are multiplying it by 4 minus square root of 5. Can you clearly see that this is A, this one is A, because it's also A here? Can you also see that this is B, and this is also B here? And the sign in the middle is minus, and the sign is plus, but they are all multiplying. So the signs must be different. They might be opposite, positive and negative, and then they are all multiplying. So signs must be opposite, they are multiplying, but the numbers are the same. Then this is different. It becomes a squared minus b squared. What is the a squared there? Is the 4 squared, because a is 4 minus the b. What's the b? The b there is square root of 5, and we are squaring it, and then we are going to get 4 squared minus square root of 5 all squared. This gives us 16. This gives us 16 minus 5 to the power half. Do you remember? Before this squared, and this will cancel that. So you have 16 minus 5, and that gives you 11. All right, that gives us 11. So please do not forget that. Please do not forget that. Now, we're also going to talk about rationalization of a surd. We're going to talk about rationalization. If you are told to rationalize the denominator or rationalize the surd, it means you're going to change. So let's say you have, let's say we have something like 2 divided by square root of 3 minus square root of 2. We want to rationalize, we're going to multiply this by the denominator, which is square root of 3. But the sign has to change to square root plus. Divide the square root of 3 plus square root of 2. And when we do that, we're going to have 2 divided by square root of 3 minus square root of 2 times square root of 3 plus square root of 2 divided by square root of 3 plus square root of 2. And we're going to multiply the top, right? We're going to multiply the top is going to be 2. The top is going to be 2 multiplying the square root of 3 plus the square root of 2 divided by the square root of 3 minus the square root of 2 together, and the square root of 3 plus the square root of 2 together. Remember, we're just multiplying the numerators 2 by all of this, and then this whole thing by all of that. That's what we are just doing. Now, you can see this and this are the same. The A is also the same as that. So we applied what we studied. Okay, don't let us throw it away. So here, the top part is going to be this 2 is multiplying this, we get 6. This 2 is also multiplying this, we get plus 2 square root of 2. And then we divide it by square root of 3 squared, okay, minus square root of 2 squared. I hope you see that, because it's different. This A, this B, this A, this B, and they are all multiplying. The sign is different in the middle, so it's difference of 2 squared. So we're going to end up having at the top 6 plus 2 square root of 2 divided by 3, because 3 to the power half squared, minus 2 to the power half squared. And we're going to have 6 plus 2 square root of 2 divided by 3 minus 2. 3 minus 2, and we're going to have 6 plus 2 square root of 2 divided by 1, which is 6 plus 2 square root of 2. And there you have it. All right, so that's the rationalization of what is said, okay? We are given any question, the denominator should change. This one, we'll multiply, the sign changes here. We'll do the same thing at the top, the same thing at the bottom, and then we use multiplication from there. I think that I'm going to bring this to a close. That's the maximum you're going to ever see when it comes to search. I don't think there might be any other tricky questions that we're going to. But if there are any tricky questions, be looking out for our shorts. Our short videos will be putting out a lot of practice questions on any topic that we treat. But I thank you so much for joining us. But as always, please, if you haven't yet subscribed, please do us a favor and subscribe, so that we can grow this channel together as a family and be able to help as many people as possible. All right, if you're already a subscriber, thank you so much for supporting us. But I'll come to you another time. Take care and bye.